welcome, and I'm glad to see you all here. As was already mentioned, the journey started at TUG 2019, where we investigated the effectiveness of hyphenation patterns and how, and essentially found that they can be used even for lossless compression, and that you can push the algorithm much further now that computers are fast enough, and now that pattern size is not that much of an issue. Yeah, you can probably see a lot of the people who are here in this picture too. Then at TUG 2021, we introduced one set of patterns for two languages, Czech and Slavic. These are already live in Chromium, Android, and I promised to myself that I will finally propose them for into TUG-, and discuss adding them to the TUG distributions. And in last year in Bonn, we developed joint patterns for 9 languages to investigate how to verify that it's possible to hyphenate unrelated languages correctly. Yeah. And now I'll be sharing what I did to fix the inconsistent quality of patterns across Slavic languages. Even though the pronunciation on which hyphenation is based is very similar, the patterns for some languages are really good, and the patterns for some languages are not that good. And we can do better, I think. So this is the contents. Let me start with introducing how hyphenation patterns work, to refresh you, perhaps. So patterns can be thought of as a early word. I mean, often even the big models of today are called just pattern matchers. You can understand patterns as an the hyphenation patterns as an early machine learning approach. So what these hyphenation patterns actually are. As you can see in this example, it's shown what patterns would be used to hyphenate the word hyphenation. The 3 here, odd numbers permit, even numbers forbid hyphenation. Therefore, the 3 here says with a low priority, you should probably hyphenate here. And you maybe should not hyphenate between these 2 sets or strings when you find these in a word. And you definitely should hyphenate here. So higher priority means, yeah, higher numbers mean higher priority. The patterns are also as short as possible, and this affords them some significant generalization properties. And the patterns compete with each other. Instead of one big set of patterns, we use these layers that are actually generated one by one. So if we want to actually hyphenate the word hyphenation, we look up all of the substrings, and then for each of the spaces between letters where we could theoretically place a hyphen, we then find the highest number of allowable, and from this it follows that we should hyphenate here, here, and nowhere else. So how do we generate these patterns? In, I think, 1970 something, Liang had to generate a way to generate less than 5,000 patterns to hyphenate English. This is done in layers, as I said, and in every level there are some parameters, and they set first how long the patterns that should be considered should be, and what's the threshold to reach to let this pattern into that level. This is the score for a correctly hyphenated place, and this is the score for a incorrectly hyphenated place. So if there is a pattern that's being considered that, let's say, would cause 1 incorrect hyphenation in the whole training word list, and 23 correct hyphenations we decide to include because 23 minus 2 times 1 is 21, which is more than 20. And we go like this level by level, remembering that odd numbers permit and even numbers forbid hyphenation. The generation required an hour of CPU time on this old computer. Now it's reasonably fast, but also the word lists are much bigger. We use word lists that are approximately 10 times bigger these days than the Pocket dictionary. So, as I already hinted, the Python program can be thought of as a machine learning program. The generic pattern has minimal length, meaning they afford generalization properties, which are very useful for hyphenation on out-of-vocabulary words. We need hyphenation on out-of-vocabulary words not only, mostly because languages develop and we want the patterns to stay relevant if possible. As I mentioned, at TUG 2019, we shown that we can even tune this algorithm to be lossless and reach 100% coverage and no errors. And we can do that also for 2 languages. I should also introduce TUG-, which is the canonical source and repository for hyphenation patterns for most software, actually. It's used in TUG, web browsers, LibreOffice, Android, and Kindle uses Android, and it even uses these hyphenation patterns as far as I know. So let's look on a bit of a higher level at hyphenation. Usually, hyphenation is phonology-based. It mostly used to be etymology-based. For British English, etymology-based hyphenation is still preferred, but there is a clear trend towards syllabic hyphenation in essentially all languages. Across the Slavic languages, there are languages where the Institute of Language says that etymology-based hyphenation should be used, but in schools, children are taught to hyphenate syllabically. There are also, according to the phonology, because it's really hard to teach children etymology, right? So currently, mostly, it's primarily syllabic, but morphology is also important in the case of compound words. And also, it's very important in the case of foreign words, which you also need to hyphenate, often because these are, because these are for long, and they are occurring more and more often in formerly monolingual texts. So why do we need these syllabic patterns? This is an extravagant example of why these are useful. I think this text looks a bit better, even though the lines are probably still too small for words this long, but it's much more pleasant to look at and probably also read this text compared to this text. And the importance of hyphenation is not reducing these days, because whereas we don't read text from narrow columns in printed daily or daily papers, we read a lot of text on other tiny rectangles. So, yeah, I mostly mentioned this already. And we know that we can generate with no hyphenation collisions, since there are almost no words that have different hyphenations in different languages. So how did I go about improving these patterns for languages that don't have great patterns? So the pronunciation for Slavic languages is very similar, but the orthography is different. This is Ukrainian, this is Czech, and this is Polish. These are pronounced very similarly. I'm not sure about the Ukrainian, but the Czech is Praha, and the Polish is not entirely Praga, but something in between. But still, these are very similar, and especially in the case of Ukrainian, it's the orthography is different, but the pronunciation is actually very close. Therefore, the hyphenation is also very close because it's based on pronunciation. For this, we use the International Phonetic Alphabet. You might know it from your English textbook. It represents the pronunciation of each of the words, and the characters roughly correspond to phonemes. These characters are actually stresses or stress markers, so International Phonetic Alphabet. Yeah. So before we dive into the approach, we need to set the goals, and the approach is set by the anti-goals. So these are things that we don't want to do, and that quite limits the maneuvering space we have. I don't want to exert my opinions as a non-native speaker into the resulting patterns. So even if I see something that I think is clearly a mistake, I will not fix it because I don't feel qualified for that, because this is not a language that I can speak, mostly. And we also don't want to improve already good patterns because we don't have the data for it. And the goals of this are different. The goal is to improve patterns for languages with no or subpar current patterns. And also we want to deploy the methodology for pattern development through transfer learning for several languages in one language family, so that this can be potentially also used for other language families. So how did we actually implement this approach, and what methodology did I choose? So this is the big diagram that we will go through step by step. Essentially, we start with a data set from Wikipedia. I will explain why I had to choose this data set. Then we hyphenate the words from Wikipedia with the current patterns. Then we convert them to IPA. And then we weigh these specific word lists to generate joint IPA patterns. And then we use these to hyphenate these words again with the new patterns, keeping in mind that we trained these weights for the generation, and then we generate and evaluate the resulting single language patterns, which operate directly on the resulting orthography and not on IPA. So for the start, we need a bunch of words in the target language. It's actually surprisingly hard to acquire clean single language word lists. Previously, for Czech and Slavic, lexical computing used to provide us with these data sets, but now they are unwilling, and most importantly, reproducibility is very important, and therefore I opted for Wikipedia. It's a clean word list, but colloquial terms are not that represented there. It's open for discussion whether it would make sense to introduce some other word lists into the mix of the data, but yeah, but I hope that the Wikipedia dataset will be sufficient, given that most of the other patterns are still generated from mostly dictionaries. So we now have hyphenated words in the source orthography, and we need to transfer them to IPA. We use eSpeak for generation of IPA, not because the eSpeak subset that it used would be very rich, but because it's very consistent across 127 languages, so it covers all of the languages we need. But the transfer is actually not that trivial. The task in this case is to transfer the hyphens from the word in the original orthography, and if we have the IPA word,
without the hyphens, we need to decide where do we put these hyphens. We cannot just convert this to IPA, this to IPA, this to IPA, this to IPA, because the IPA depends on the surrounding characters. There are 1,065 possibilities of where to put them. In the end, we opted for this approach, where we first compute a Yarrow-like simulator score, which essentially computes how many letters are on the left side of a candidate pattern in the original, and how many are on the left side of the. So let's say we evaluate placement of this hyphen here. So we see that the corresponding pattern, the corresponding hyphen, meaning the first hyphen, is here, and we see that all of these match, and some of these to the right match, and we compute a score for that. Yarrow is actually an optimization over the Levenshtein, because not only is the complexity a bit better, the constant factor is also a big factor, and it's quite a bit faster. The important thing here is that this scales with the length of the one word and the number of hyphens, whereas this scales with the length of the word times the length of the original word. And if there's still tie, we convert each syllable to IPA and perform this once again. So now we have the IPA hyphenate word lists, and we need to generate these joint IPA patterns. We know that the patterns can learn the IPA well. Maybe it's surprising to why is this not 100%. The answer is I could tune them to be 100%, but then I would probably overfit, and this is an example where I'm probably already overfitting. And if I had not had as an anti-goal to exert my opinions and thoughts into the patterns, I would definitely look into these wrongly hyphenated places, as these are great candidates for errors in the underlying word lists. So yeah, the challenge is not to overfit, as they can infer the language and then reproduce the original errors in the original word lists. So how to pick these weights? And again, I can't just ballpark them and think, okay, the check patterns are really, really good, so I should weight them a lot. So we need to find what set of weights works best for the performance of the resulting patterns. We need some kind of ground truth to know what is the actually correct hyphenation to be able to tune this. And we also will need ground truth to validate. So this is at the end, when we already have optimized the weights, we need to decide, are these patterns good enough? And are these patterns definitely much better than the previous ones? However, there's a severe lack of definitely correctly hyphenated words. Very few languages provide hyphenation, and very few language institutes provide hyphenated words. If you know a good source of hyphenated word for your Slavic language, I would appreciate it. This could be a dictionary or something else. Some languages have Wiktionary or somewhere. So to avoid grid search in the parameter space or weight space, we train a surrogate model and sample weights from that. We sample candidates' weights that we then evaluate. Therefore, we just avoid the grid search. You can think of this, again, as an optimization over grid search. So then we have the new IP hyphenated patterns. The approach is similar to the transfer from the original to the IPA, with a few more challenges that I don't have time to go into. And so this is what the final single language patterns are. The generation in the end is quite similar, or quite simple, but it's very hard to evaluate. This is probably the approach that I will settle with, and even though it's not optimal, I don't see a better way to do this, especially in the severe lack of definitively correctly hyphenated words. So this is the methodology we used. And let me jump to the conclusion. It is feasible to significantly improve at least current Polish, Croatian, Serbian, and Ukrainian patterns. And I think this is applicable to other language families. I have released a reproducer workflow for this, and the resulting single language patterns will be submitted to Hyphen by the end of the year. As I'm kind of running out of time, thank you for your attention. If you know a source of good hyphenation data for your Slavic language, do reach out. Do you have any questions?
Okay, thank you for the talk. We have actually enough time for the discussion, so Nelson, yeah.
I wonder if it might be possible to get the collaboration of Google and the Google Books project to identify books in Slavic languages published before computer typesetting, roughly 1970. Extract from those all of the hyphenated words and see how they match with your algorithm. Because presumably those were done by competent typesetters in every country who were probably quite skilled at hyphenation, even though there certainly could be mistakes, but it might be possible to get a rather large corpus of hyphenated data that way.
Yes, thank you. I think that's a really good point, and I will probably definitely use this for the ground truth data, because I can just look into old books and take the hyphenated points as correctly hyphenated points. As for the collaboration with Google, that seems like a long stretch, but I will consider it if the other data doesn't seem sufficient.
Boris?
Yeah, this is not from YouTube, it's from me. IPA has a character you mentioned, which is not normally in typography, which is stress. And while stress in some languages is fixed, like in Polish, in some languages it's flexible. So did you see whether hyphenation patterns are influenced by stress position? Did you take a look?
I haven't looked at that, but I mean, mostly, oh well, yes I did. I stripped the stress markers, and in one evaluation I found that they perform slightly worse. And I think this kind of makes sense because the stress markers are good. Usually around the stress markers you would put a hyphen, right? So I did find this in one run, but it's nothing I can definitely say that holds.
You might want to take a closer look because linguists probably would be happy to know about this. Thank you.
Thank you.
Any other questions?
In searching for good word lists in the multiple languages, have you considered, in addition to Wikipedia, proceedings of national legislatures that are published electronically?
Are these, do you mean published before the advent of computer typesetting? Because I think most of them will be actually just typeset with Microsoft Word.
Well, presumably they used to publish them without computers.
Yes. Still, the issue with this is that I would find I need to find all of the possible hyphenation points in a word, and therefore it's not sufficient to just find the word hyphenated in one place. But I need to find it hyphenated enough times to be reasonably sure that I found all of the hyphenation points. But yeah.
Yeah, we have still time for another question or comment.
With every language set of patterns, there's always an exception word list of words that are difficult to hyphenate or would be misinterpreted if they were hyphenated at obvious breakpoints. One I happen to know of is the word white space in English. Two words run together. TeX by itself hyphenates it as white space, but it really is white space, and so it's in the standard hyphenation exception list. Have you compared the lengths of the exception lists in these several languages that you support, say with other languages, as perhaps a guide to how accurate the hyphenation algorithm is working?
These exception lists are usually there are not many languages that have these that have these exception lists. I think English is the most prominent one. And I think we can think of the last level of the patterns as a exception list, because in one of the slides that I can't show now, in the last level we very much penalize any wrong hyphenation. So you can think of that as the exception list generated automatically.
Last call for comments, questions. Maybe just short comments. When one generates the patterns, you may set up the parameters so that you may filter out those outliers or specific exceptions, so that it's enough. The estimation is that small hundreds of words has to be filtered out this way and checked and modified, and in the final run generate the perfect patterns that cover even the exceptions. And the exceptional words are in that way into the word list, and in the following runs convey the information.
So thank you for the question, and thank you for your attention again.
Yeah, thanks, Andrew.